With the intro out of the way, now let's get started with some real cryptography. In particular, we start with symmetric cryptography. Now, symmetric encryption uses a single key to encrypt the plaintext and decrypt the ciphertext. So we're going to discuss asymmetric cryptography later, and there you have different keys. So the symmetricality is the fact that the key is the same. Now this key is shared between Alice and Bob. Both of them know the key, but Eve does not. So this is exactly the situation that we've seen so far, and this is also known as shared key or private key cryptography. And private key here refers to the fact that the key must remain private. So in asymmetric cryptography, we can expose one of the keys without endangering the security of the system. Now, symmetric cryptography can achieve some particular properties, and first of all, I would say it's fast, compared at least to asymmetric cryptography, which means that symmetric cryptography is also the workhorse of cryptography. If you have a lot of data to encrypt, this is what you use. So, symmetric cryptography protects confidentiality. So if you change a plaintext into a ciphertext, then without knowing the key, you should not be able to recover the original plaintext. But also, symmetric signature schemes exist that provide integrity and authentication. So what's missing? Non-repudiation. You cannot do non-repudiation for the fact that the key is shared. If Alice can put a signature, then Bob needs the same key to validate it, which means that Bob would be able to write the same signature, and hence non-repudiation is not possible. Let's start with the simplest possible symmetric algorithm, which is the one-time pad. Now the one-time pad assumes that we have a message and a key that have the same size. You can perhaps already realize that this is not very practical, but it gives you some interesting properties, as we will see. So here we assume we have a message M, which has n bits, all numbered, as shown here using the subscript, and an n-bit key, numbered in the same way. Now what can we do with this in terms of crypto? We can perform a very simple encryption scheme where we XOR the message with the key. So we use the exclusive OR operator for each individual bit between the message bit and the corresponding key bit. Okay, so the ciphertext is the message XOR the key, and now decryption can be done very easily in the same way, namely by XORing the ciphertext with the key to yield the plaintext. Why does this work? Well, that's actually pretty simple. The ciphertext XOR the key is identical to the message XOR the key, because we fill in the value of the ciphertext as specified above, XOR the key. Now any value XOR itself is automatically 0, and anything XOR 0 is the original. So we get back the original message by XORing with the key twice. Of course, if we XOR with something else, we get complete garbage. As simple as a one-time pad may be, it provides something that none of the other algorithms that we discussed can provide, namely perfect encryption. This is only possible under the following assumptions, namely that we never ever reuse the key and that the key is actually perfectly random. Now, if we follow these rules, the one-time pad provides perfect encryption in the sense that the ciphertext leaks no information whatsoever about the original. For example, if we find that there's a 0 bit in the ciphertext, it might be equally likely 0 XOR 0 or 1 XOR 1. If we start trying to brute force the message, we will simply get back every single possible message. So the ciphertext does not give us any information about the original plaintext. Now, it is important to note, whenever the key is reused, this completely breaks down. If we have a known plaintext, for example, then we get the key very easily. In a known plaintext attack, we simply XOR the plain text and the ciphertext. And we get back the key, because this is how XOR works. If we have two known ciphertexts, we cannot necessarily leak the key, but if we XOR them together, then the key drops out, and we get the XOR of two messages, which is of course also an important leak. It can provide information about what was in the messages. In particular, it shows which bits are the same and which bits are different. Unfortunately, the one-time pad isn't really practical. Because the key must be as large as the message, the key size tends to be huge compared to other algorithms, and moreover, we cannot reuse the keys. So we must find a way to share these huge keys between the parties without sending them over the network. And this is super impractical. It's something we can't really do in practice. So we don't really use the one-time pad normally. Instead, we can use a pseudo-random number generator to generate the key. Now in this case, the initial seed that determines what the sequence will be that the pseudo-random number generator generates becomes the real key. Now this approach is simple and very efficient. So it's known as a stream cipher, and these are very fast. However, not every stream cipher is really strong. In particular, WEP, the wired equivalent privacy, was an original protocol used for Wi-Fi encryption. And this was badly broken. And this was also a stream cipher. So it's not necessarily the case that every stream cipher is bad, but the construction is somewhat risky because it's a very simple construct and is hence relatively easy to analyze. Most of the time when talking about symmetric encryption, we're talking about block ciphers. These are the typical way to do it, and I already hinted at this when talking about the Caesar cipher. If you take multiple characters at a time, you can make a better encryption algorithm. Now the idea is very simple. We divide the data into blocks, of course, because the block has a particular size, say 128 bits. We get far more combinations than if we do this character by character or even bit by bit. So brute forcing becomes harder. And now what we do is we have a function that performs a computation using the key to map each block of plain text into a block of ciphertext. This is the encryption operation. So there's a simple mapping depending on the key from plain text to ciphertext for each individual block. And this function must be reversible. And the reverse function is used for decryption. This is very widely used. It used to be used especially in the context of the DES algorithm, which was for a very long time one of the most prominent encryption algorithms. However, it's interesting to see that the key size was very small compared to what we use these days. So there was a 56-bit key size. And what was interesting was that when the DES cipher was actually designed, the authors got feedback from NSA to determine whether the system was secure or not. And NSA actually required that the key size be reduced. Presumably this was because they thought they would be more capable of breaking this when people used it. But the NSA did also actually find a weakness in the approach used in DES. A more state-of-the-art algorithm that has larger keys and larger blocks as well is AES, which is nowadays, I would say, the standard symmetric encryption algorithm and very widely used. As far as I know, this algorithm is still considered to be secure. Let's use a block cipher and see what happens. On the left, you see an image, and on the right, what I've done is converted this image into raw pixels and then encrypted it using a block cipher. What we should expect if we encrypt something is random garbage, because if there's something of a pattern, it means that it's revealing some pattern in the plain text. If you look at the image, this is very obviously the case here. We can clearly still recognize the letters as well as the VU chicken, even though we've encrypted every single block. The issue here, of course, is that the mapping is the same from block to block. So every single block that contains only white pixels will be mapped to the exact same sequence. Now this is a problem because it means that the ciphertext is leaking information about the plain text, which of course we don't want. We need to find another way to use the block cipher such that we don't get these nasty patterns. The approach I just showed you, which is more or less the obvious approach to use a block cipher, is known as electronic codebook, or ECB. Now this approach, as we've seen, still reveals repetitions, which means that confidentiality is not ensured. Moreover, you can also reorder the blocks. So if you have some knowledge about the content of the blocks, then you have an issue. You can reorder the blocks, or the attacker can reorder the blocks and create a new message. So, if we use electronic codebook, we have no confidentiality and no integrity, or at least not guaranteed completely. So we need to do something else. What we do is called cipher block chaining, or CBC, which means that we chain every block to the previous one. For the first one, of course, there's no previous block, so instead what we use is something known as an initialization vector, or IV. Now the initialization vector does not need to be a secret, but should not be reused. If we reuse it, there's a risk that we can tell whether messages start with the same blocks, which defeats the purpose of what we're doing. So this is the CBC approach. So what we see is that each block is handled a bit differently with feedback from the previous block, or in the first case from the IV. So what happens is this: we take the first block of plain text and then we XOR it with the initialization vector before we encrypt it. Now, we perform the encryption and the output is the ciphertext. However, the ciphertext is not just sent as an output to the message, but it's also reused. And then it's XORed with the next block of plain text. And this continues on and on. Now at this point, the input for the encryption function depends on the previous block, or in case of the first block, the initialization vector. At this point, we no longer have the situation that identical blocks yield identical output, because after the XOR they will all be different in practice. To decrypt data using cipher block chaining, we do the opposite. We start with the ciphertext. We immediately apply the decryption function, and only then do we XOR the result with the previous block or the initialization vector. Now the nice thing here is that we know the previous block or initialization vector in advance. It does not depend on the decryption function. So what is nice about this is that we're still able to decrypt blocks in parallel, because we know all the inputs that we need. Now, if we do cipher block chaining and we encrypt the same image, we get what we originally hoped to see: an image that looks completely random. So the image now no longer reveals information about the original image. One other complication of block ciphers is the fact that the input must be a multiple of the block size. If it's not, then the last block will be incomplete and we cannot encrypt or decrypt it. To make this possible, we have to pad the block. So we have to add some data to make sure that it ends up being a complete block. Now, the obvious choice would be to simply append zeros at the end. However, this is not a good solution. Take a moment to think about why. Why is this not a good solution? This is because this makes it impossible to recover the original. If the original message ended in zeros, we are unable to tell the padding from the message. So this is no good. What can we do instead? We pad with bytes, each containing the length of the padding. So if there's 4 bytes of padding, we repeat the byte 4 times. Additionally, we make sure to add 1 block of padding, even in case we have a multiple of the key size in the message. Right, so even in this case, we don't really need the padding, but we still add this block to be able to uniquely identify the length of the message. Otherwise, if the final block ended in something that looks like padding, we would drop it off from the message, and this is not good. In practice, cryptography libraries automatically add the padding where necessary, but there can be multiple ways to do padding. The one I described here is just one of the more common ways, and you may have to specify what type of padding you want. Now to give some example, take the data we have here. So we have 8 messages on this slide and we want to pad the messages to a multiple of the lengths. So looking at the first message, it's 9 bytes long. We can see that the block size is 8 bytes. So how much padding do we need? We need 7 bytes. Now the padding value is 7 and we added 7 times to pad the message to the right length. And now it's a multiple of 8. For the next one we need 6 bytes of padding, all of which again use the value 6. The remainder works just like that, except for the final one. In the final one we already have a multiple of the block size, but we still need to add the padding to be clear about what is in there, so we add it as a separate block. Now this is the only case where we really waste any space. As I mentioned, we don't go into a lot of detail in this course about cryptography, but we do want to present the padding oracle attack, which is a really interesting attack, hence why we included it as an example of what you could do to actually break a cryptographic algorithm. The assumptions for this attack are that the attacker is able to send an encrypted message to the server, that the server will decrypt this message and return an error if the padding is incorrect. Now this seems kind of weird perhaps, why would you include this particular case as an exception, but it turns out that this was handled specifically in this way by libraries at some point, which meant that they were returning information, revealing information about whether a failure was caused by the padding being incorrect. And then the server must also use a block cipher, using cipher block chaining. Under these conditions, we will show how the attacker is able to decrypt the last block. And of course, if you want to decrypt more, you can make another block the last block, simply by dropping the remainder of the blocks. The only one that you cannot do is the first block, which uses the IV. To show how the attack works, I will use the following notation. D_K means to decrypt a block using the key K. N will refer to the number of blocks of ciphertext. PI and CI, respectively, refer to the plaintext and the ciphertext block with an index I. Now, if we think back about the decryption scheme for CBC, look at slide 12 if you forgot, then we get the following formula. So Pn-1, so this is the last plaintext block, is found by decrypting the last ciphertext block and XORing it with the ciphertext block right before, so at position n-2. Now this means that if we change the penultimate block of ciphertext, so not the last but the one right before the last, it means we change the plaintext that the server will see for the last block. And this is very predictable because they're using an XOR operator. Now at this point, based on the assumptions I mentioned, the server will check whether the padding is still correct. So we can corrupt the plaintext that the server will see, and for particular values it will tell us that the padding is now corrupt. This leaks information about the plaintext that you get, and because of the simple structure, the fact that we're using XOR, this is very predictable. And we can use that to decrypt efficiently the entire block. Now let's take a look at an example. Let's say we have 16 bytes of ciphertext encrypted with DES using 8-byte blocks. Now we will write the bytes of ciphertext as C0 up to C15 and the bytes of plaintext as C0 up to P15. Now, what we can send to the server is the following. We send the ciphertext, but on the 8th byte, that is byte number 7, we XOR it with the value B. And value B takes any value between 0 and 256. Okay? If we send this, we can figure out which of these values result in a correct padding. Now, C7 is relevant because it's used to compute P15. Right? We have the block size of 8, so we look back 8 bytes to get to the penultimate block, which is used for the decryption, for the XORing and the decryption. Now let's say that only B equals 0, so an unmodified ciphertext, and B equals 2 actually work. Now, the unmodified ciphertext is obvious. It should work because the original ciphertext is correct. But it's interesting to see that if we change the value by XORing with the byte 2, it still works. So this means that XORing it like this actually yields a valid padding. In particular, it means that if we perform this XOR, we get a padding of length 1. Right? So this means P15 as the final byte of plain text XORed with 2 equals 1. Now we can easily derive the value of P15 from this. We know that it is 1 XOR 2, which is 3. So we found the final byte. Now, this is at least a good start, because we now know that the final byte of the original block was 3. This provides a lot of information because the 3 is also the length of the padding. Right? In every case, the final byte is the length of the padding. So now we know that the plaintext has 3 bytes of padding, and the 3 final bytes of the plaintext are all 3. Now we can figure out the next byte. So let's send the plaintext that is listed, the ciphertext that is listed here. So what we do is we XOR all the bytes of real padding with 7. Now 7 is 3 XOR 4. That is the plaintext value of the padding, which is length 3, with the padding that we want to achieve, length 4. Now we want to figure out which value of B will yield a plaintext that has the value 4. Right? So this would be a valid padding, and it would stand out because we can use the server as an oracle here. The error message that we get indicates what is the issue. Now, let's say that only the byte hexadecimal 36 actually works there. What do we know then? We know that if we take the actual plaintext and XOR it with this particular value, we get 4. Because only 4 should work if the padding is 4 bytes long. So we can derive the value, which is hexadecimal 32, or the ASCII character 2. We're leaking more and more information here. Next, we try to create a message that has a padding of 5 bytes. So what we do is we XOR all the bytes that we know with such a value that the eventual plaintext the server sees becomes 5. Right? So we XOR the ones that had a 3 in there with 6, and we XOR the one where we found the digit just now with hexadecimal 37. All of these yield a padding byte of 5. Now again, we tried multiple values of B, every possible value that can fit in a byte, and look until we find the one that works. Now for this one, we know that the plain text seen by the server after modifying the bytes will be 5, because it will have to match the other bytes of the fake padding. Now, let's say that if only hexadecimal 31 works, then we must XOR it with 5, which is the length of the padding that we're pretending to have here. And we find that this byte is hexadecimal 34, or ASCII character 4. We can use the same approach, and I will leave this as an exercise to the reader, to figure out what the other bytes of the ciphertext actually are. And we find that the values are like this. So now we can take a look at the values that are found. So we have the bytes, we have the padding, and this results in the plain text. Now, we figure out that the plain text is ER space 42, followed by the padding of 3 bytes. Okay, so this is a simple matter of XORing the byte that we found to work, so the value of B, with the padding length at that point. And this allows us to recover at least part of the original message. This means that cipher block chaining is not secure when used like this. You need to use another algorithm to make sure that this is actually secure. It also is actually an interesting way to show how crypto algorithms can be broken in very non-trivial ways. As a final topic for symmetric encryption, I will discuss symmetric signatures. The signatures are important in the sense that they allow you to make sure that you can show that the message was sent by someone. Right, so we show that the message hasn't changed since it was sent by Alice. Now, symmetric signatures are also known as message authentication codes, or MACs. Now, they are constructed in such a way that if the message changes, the MAC is no longer valid. Obviously, typically this depends on the hash algorithm. Also, the key is needed to be able to generate a valid MAC. If we didn't need a key, the MAC would be useless because we wouldn't be able to check whether the person who made it actually had the knowledge that they needed. And finally, for a MAC, the same key that is used to generate it is also needed to verify whether the MAC is valid. Now, this scheme has properties as follows. Integrity holds because the message cannot be altered without changing the MAC, which will be noticeable. Authentication is also achieved, so we know that the MAC was generated by someone who had the key, which authenticates that person. However, non-repudiation is not possible. We use the same key to verify as to sign, which means anyone who can verify can also sign. So they can never claim towards a third party that they were not the ones to sign, but that the other person was the original person who signed. Right? So non-repudiation is not possible here. HashMac or HMac is a typical implementation of MAC. So MAC typically uses hash functions because it's really convenient as a way to summarize the message. Now, how to do this is actually very simple. Signing with an HMac means that we need to combine the key and the message and then apply the hash function. And because of the properties of the hash function, we are unable to recover the message and the key from that. And changing the key will completely change the message. Right, so Alice combines the two, for example using concatenation, and then applies the hash function. The result is the signature. Now Bob can also compute the signature, because Alice and Bob share the same key, and then Bob can verify whether it's the same one that he received from Alice. Now this shows how a symmetric key signature can work, but still we cannot provide non-repudiation. So for this property, we need to think about asymmetric algorithms, which will be the next topic.